Nick Abbott, who, in the interests of reducing transatlantic air traffic and for the environment, has agreed to give a remote lecture, even though he'll be in Cambridge next week or the week after next. And his topic today is endotoxin-induced ordering transitions and liquid crystalline droplets. Nick, the floor is yours.
Okay, so thanks very much for the opportunity to give this seminar. And please pipe up if you have questions during it. I'm happy to address them on the fly, and also tell me if what I'm saying is not audible. So as Mark indicated, I'm going to talk about some recent work we've been doing on endotoxin-induced ordering transitions in liquid crystals, and this effort is part of a broader program of research that we have exploring the use of liquid crystals and surface-driven anchoring transitions as the basis of design of stimuli-responsive materials, and particularly soft materials that will respond to the presence of biological targets. And so we have, over the past decade, published a number of papers in this spirit. And more recently, we have been intrigued by the use of liquid crystals in confined geometries in that context, and that has led us to look at liquid crystalline droplets. And so to put the work into sort of a broader context, I'll go to slide 2 and say that what I'm really talking about are oil and water emulsions. And so this is a topic that has, of course, received a lot of attention. And despite effort that's been invested in understanding even these relatively simple isotropic oil-water systems, there's no shortage of mysteries. And what I'll tell you is that some of those reappear in our work with liquid crystalline oils. And in particular, one mystery is what happens in terms of the charging of the interface between a non-polar oil and an aqueous phase. And so these are systems, of course, that are characterized by the presence of ions. Water can dissociate. And if you apply an electric field across, so a DC electric field, across a dispersion of non-polar oil droplets dispersed in water, they'll migrate in that electric field. And so there's an accumulation of excess negative surface charge that appears at oil-water interfaces. And that accumulation is not well understood in isotropic oil-water systems, but it also manifests itself in some of the phenomena that I'll tell you about involving liquid crystalline droplets. So I'm going to be talking about what is a relatively simple liquid crystal, and that's a pneumatic. And I'll confine my comments today to 5CB, and so a single component pneumatic that exhibits long-range orientational order at room temperature. And so relative to droplets of isotropic oils, when you have long-range order, there are a number of additional considerations that you have to incorporate into your description of these oil dispersions. So one is surface anchoring, and so this is surface-induced ordering of the pneumatic. And the range of sort of energetics, or the order of magnitude of the energetics that characterizes surface-induced ordering in these low molecular weight pneumatic systems is, and I'm on slide 4, around 10 to the minus 3 to 10 to the minus 2 millijoules per meter squared. And when you have an isotropic solvent like water in contact with the pneumatic, the anchoring energies lie on the lower end of this range. And so our estimates for the 5CB water interface, it puts them around a microjoule per meter squared. So in addition to surface anchoring, you have the elasticity of the liquid crystal, and the configurations assumed by liquid crystals within droplets reflect the competition often between the surface energetics and the energy that's stored in the strain states of the liquid crystal, and a typical modulus for a strain of a low molecular weight nematic is somewhere around 10 to the minus 11 newtons. And then finally, in confined geometries, depending upon the boundary conditions, it's not always possible to accommodate those boundary conditions through continuous strain, and so that leads to the introduction of discontinuities in the director or topological defects. And so in the phenomena that I'll describe today involving endotoxin, all three of these attributes of the confined liquid crystal are important. So in dispersions in water,
are you on the slide?
Yes, slide 5, sorry. Slide 5, so if you disperse 5Cb in water, in the absence of high concentrations of electrolyte in the water and around ambient or physiological pH, so around pH 7, the easy axis of the 5Cb is tangential to the interface. And so that interfacial anchoring gives rise to the bipolar configuration in droplets of 5Cb that might be, say, 10 micrometers in size. And so you have this internal strain as indicated here, so bend and splay, and you have the presence of two surface defects, so-called boojums. And so this is what you'll see in the absence of any adsorbate on the interface. But if you do add a surfactant to the aqueous phase, you can change the anchoring of the liquid crystal such that the easy axis is perpendicular to the interface, and what you'll typically observe in that case is the formation of this so-called radial structure. And so if you titrate in a surfactant, so if we go to the next slide, slide 6. So if you titrate in a surfactant, and the surfactant here is an anionic surfactant, so it has the sulfate head group, sodium dodecyl sulfate. So it will adsorb to the oil-water interface, or the interface between the nematic and the aqueous phase, and will, at saturation coverage, ultimately trigger this radial transition. And so this configuration is being driven by surface anchoring. And the surface area on this droplet, so it has a diameter of about 8 micrometers. So the surface area of this droplet is of order 100 square micrometers. At saturation coverage, where you see this configuration, each SDS molecule occupies an interfacial area of order a square nanometer, a bit less than that. And so in order to achieve saturation coverage, you need something like of order 10 to the 8 SDS molecules per liquid crystalline droplet. And so that's the order of magnitude of the number of adsorbates required to trigger this transition. And so between the two extremes, the bipolar configuration and the radial configuration, there are a number of intermediate states that you can see here. And so this is a series of optical micrographs. These are bright field micrographs recorded as SDS was added to the aqueous solution and the configuration of the droplets were allowed to equilibrate. So these are, as far as we understand, equilibrium states which occur as a function of the surface concentration of the surfactant. And so what you see first at around 0.2 millimolar of SDS is the appearance of a disclination ring. It moves towards the poles. You see the appearance of this so-called pre-radial defect or configuration. And then that moves ultimately off the surface towards the center to form the radial configuration. And so this series of states that takes you from the bipolar to the radial is something that we see in numerous surfactant and amphiphile-based systems, and it's associated with a configurational transition that's driven by changes in surface anchoring. Okay, so that's sort of the characteristic. So that's SDS. Slide 7.
A question, yeah.
Yeah.
Is the density of the surfactant uniform across the sample for all of these configurations, or do you know?
I would guess not. So we don't know for this specific experiment, but we do know that in micrometer thick films of pneumatic 5CB, where we absorb SDS from the aqueous phase, that the strain within that thin film can drive the phase separation of SDS at the aqueous liquid crystal interface. So we see under conditions where there's substantial elastic energy stored within a thin film of the pneumatic, we see patterned orientations of the liquid crystal which coincide with phase separation of the amphiphile on the interface that's driven by the release or relieving of the elastic energy that's stored in the strain states. And that's seen both for soluble amphiphiles like SDS and also insoluble amphiphiles, phospholipids that absorb irreversibly on the surface. So the strain, which is embedded in the liquid crystal, can redistribute the amphiphiles on the surface, and we see that in pronounced ways in thin films. And if it's a topic that interests you, we've actually published a couple of papers on it. There's a physical review letter published, I think, 4 years ago roughly, describing control of phase behavior of amphiphiles using strain within thin films of liquid crystals. And in what I will show you next, so slide 7, with endotoxin, indeed we believe that the strain in the liquid crystal is controlling the distribution of this much more complicated lipid in its association with the liquid crystal. So, so this is really the subject of my talk, and so it's going to be what happens if you introduce a biological lipid into the aqueous phase. And the biological lipid is a lipid that is present in the outer membrane of gram-negative bacteria, so something like E. coli. And the cartoon of the outer membrane is shown on this slide. So the lipid is called endotoxin, and it's actually a conjugate, so a combination of a polysaccharide tail, and that's what's extending away from the surface, and a lipid. And the lipid portion is called lipid A, and it's shown down in the bottom right corner of the slide. And so it's an unusual lipid. It has 6 tails. The majority of biological lipids have 2 tails, and so it has an unusual molecular architecture. And that lipid is the component of endotoxin that our immune system responds to. And so it's a toxin. And so if you introduce it into somebody intravenously, it will trigger an immune response. And for that reason, all biomedical devices, all intravenous fluids that are injected into all pharmaceuticals are all mandated to be tested for endotoxin in the US by the FDA. And so detecting endotoxin is a very large business. It's a multi-billion-dollar business. And to sort of calibrate you on the relevant concentrations, if you go to slide 8. Yep. So what I'm showing here are the contexts in which endotoxin is measured. And so you'll see down the left side of that table, clinical context, for example, if a patient has sepsis, what the patient's immune system is responding to is the lipid A component of endotoxin as it's shed by the bacteria in the patient. If you look under the category of pharmaceutical manufacturing, you'll see that the FDA mandates that endotoxin be below a certain concentration. And I should clarify one point, that endotoxin is a polysaccharide lipid conjugate, so it also goes by the name of lipopolysaccharide. So you'll see LPS written on various slides, and that's interchangeable with endotoxin, just another term for it. And so what you'll see is that the concentration of endotoxin, or LPS, in water that is to be injected in you needs to be below 25 picograms per mil. And so that's roughly 25 picomolar as a sort of order of magnitude. And so how is that currently done? And so that's shown at the bottom of the slide. And so that image is a horseshoe crab. And so at least in the US, horseshoe crabs live on the east coast in Massachusetts, and fishermen collect them, and they're harvested and bled. And the horseshoe crab has an evolved defense against bacterial infection, and that is to coagulate its blood. And so the basis of the current FDA-approved assay for endotoxin is to take a few drops of blood from the horseshoe crab, you add your sample to it, and you see if the blood coagulates. And so that's the current technology. And so in the blood of the horseshoe crab, there's a cascade of enzymes that is triggered by the presence of endotoxin. And that cascade of enzymes is susceptible to interference. So if you had a compound in your sample that chelated, for example, with divalent ions, it will change the activity of the enzyme, and it interferes with the quantitative characteristic of the assay. With the seasons, the blood of the horseshoe crab changes, and so it's a biologically derived reagent, and that means that there's substantial variation associated with it. And so there's a lot of interest in finding alternatives to this reagent for detection of endotoxin. It's been around for about 2 decades, and while it's complicated, it's a big advance over what existed before that, and that was rabbits. So before this assay existed, the way you detected endotoxin was you injected a rabbit and you waited to see if it developed a fever. And so we'd like to see if we can find alternative ways of detecting endotoxin, and that sort of motivated the work that I'll tell you about today. So we had seen previously that synthetic amphiphils like STS, so slide 9, trigger configurational transitions, and so we wanted to see whether one could potentially detect lipid A through changes in the configuration of liquid crystalline droplets. So that was sort of the level at which we entered into the project, and we found some surprising things. And so the first sort of comment and observation based on this slide is that if you add endotoxin to an aqueous solution that surrounds a dispersion of micrometer-sized droplets of 5 cB, indeed the presence of the endotoxin will trigger a configurational transition. And so what's shown in A, B, and C of slide 9 is the bipolar state. And so that's in the absence of any endotoxin. And I can tell you also that when you have something in the picomolar range, you have to be very careful with your experiments. You have to use very clean plasticware and glassware. It all has to be freed of endotoxin, or it has to be purchased certified to be endotoxin free. And so endotoxin is everywhere, and so the experiments are not trivial experiments to do because of the sensitivity of these droplets, as I'll show you. So when you have a microgram per mil of endotoxin present in the aqueous solution, what you see is a change in the configuration of the droplets to the radial configuration. So it looks very much like what happens with STS. And this is a relatively high concentration, a microgram per mil. There's in fact enough endotoxin in that sample to almost saturate the surface of the droplets that we have in the system. So that's not really a surprising result, but it does tell us that the absorption of this lipid A, will trigger a anchoring transition. So the surprise was sort of shown here on slide 10. And so this is an experiment we did. We just kept diluting the endotoxin or the LPS and watched to see when we lost the radial configuration that was associated with the presence of the endotoxin. So what's being plotted on the vertical axis is just the fraction of droplets in a dispersion in the aqueous solution containing endotoxin that exhibited the radial configuration. And then the x-axis is the concentration. And so what you'll notice is that concentration now is picograms per mil. And so as we dilute the system, we found that we could go into the 10 picogram per mil range, and we still had a substantial fraction of the population of the droplets in the radial configuration. And as you diluted further, you saw that that fraction decreased. And so that particular plot showing fraction of radial droplets as a function of concentration was obtained with about 9,000 droplets of liquid crystal in 40 microliters of solution. If you increase the number of droplets, and that's what's being shown in the inset, by about an order of magnitude, you see that you now have a dose response to endotoxin, which is occurring in the tens of picogram per mil range, and that's actually the sort of relevant range in a technological context. So by changing the number of droplets in the system, you can influence the response of the droplets. And so that's useful from a sort of a technological point of view. And if you then do a little calculation and you ask, well, how many endotoxin molecules do I have in solution per droplet on average in this experiment, you find a very surprising result. And if you have 1 picogram per mil of endotoxin, and you have in this experiment, and I'll show you calculation on the next slide, of order 10,000 droplets, you have on average about 300 lipid A molecules per liquid crystalline droplet. So that's a very small number. And just remember to saturate the surface of the droplets, and so to trigger an anchoring transition through a change in anchoring energy, you have to have, if it's SDS molecules, something of order 10 to the 7 or 10 to the 8 molecules. So this configurational transition is not being driven by changes in anchoring energy, is one of the conclusions of our work. And so here's a very small, simple calculation, and it's really just to reinforce the message on the previous slide, and it just gives a little bit more experimental data. You know, we're typically preparing dispersions of order 1,000 droplets of 5Cb in a solution of 40 microliters. And those solutions contain 1 picogram per mil of LPS. And so if you do the calculation of how many LPS molecules do you have present, it's around 500,000 molecules in the solution. So if you take that number of molecules and you divide it by the number of liquid crystalline droplets, you have of order 300 molecules of LPS per liquid crystalline droplet. And then if you calculate the surface area available on average to each LPS molecule on the surface of a droplet that has a radius of 3 micrometers, it's an enormous surface area per molecule, so 300,000 nanometers per molecule, and it corresponds again to 10 to the minus 5 of a monolayer coverage. So it's a tiny fraction of a monolayer coverage, and it's sufficiently small that you wouldn't expect a configurational transition to result from a change in anchoring energy at that surface coverage. And that's reinforced by this experiment So we ask the question, at a planar interface, what surface coverage of lipid A is required to trigger an anchoring transition? So this is not a droplet, but it's a planar film that is stabilized. So this is slide 13. It's stabilized within a electron microscopy grid. So what we do is we spread a monolayer of lipid A on the surface of water. So it's a Langmuir film. And here the experiment is just with lipid A. It's not with the full endotoxin with the polysaccharide head. So it's just lipid A. So we then use a Langmuir film balance to control the area per lipid A molecule on the surface of the water. And what's plotted on the right is the surface pressure area isotherm for a lipid A. And at given values of the area per molecule or areal density of lipid, we pass our film of liquid crystal in the TEM grid through the interface, and so transfer lipid A onto the liquid crystal aqueous interface at known density of lipid molecules on the interface. And so if you do that experiment and you make the transfer at an area per molecule of about 150 angstrom squared, so that's the right image, you see that the optical appearance of the film of liquid crystal under the aqueous phase, it corresponds to something close to planar anchoring of the liquid crystal at that interface. So 150 angstrom squared per lipid A molecule is not sufficient to trigger an anchoring transition to a homeotropic orientation or perpendicular orientation. If you go down to something a little bit below 120 angstrom squared per molecule at the interface and you do the transfer, you see that you get homeotropic anchoring. And so the density of lipid A molecules that needs to be on the interface in order to trigger the anchoring transition, it needs to be around 1.3 nanometers squared per lipid A molecule. And if you remember that lipid A has 6 tails, so that's something around 0.2 of a nanometer squared per aliphatic tail, and that's something close to a close-packed monolayer of aliphatic tails. And so the message here again is that there's nothing magical about lipid A in terms of driving anchoring transitions. You have to have on the interface something close to saturation coverage in order to drive an anchoring transition. We're seeing configurational transitions in these droplets at very low surface coverages, and so we don't believe it's an anchoring transition that's occurring in the system. So one thing we need to explain is why do we see the configurational transition? So this is slide 14 at these very low concentrations. And the second is why is it so specific to endotoxin? So if we repeat the experiments I've just described with lipid A or endotoxin with other lipids, so lipids that have other architectures or other shapes, we see that endotoxin or lipid A is peculiar. And so if you ask what concentration of the lipid DOPC, which is shown on the bottom left side, is required to be in solution to trigger the radial configuration, you'll see that the value is something around 10 to 100 micrograms per meter squared. And that makes sense because that's the amount of lipid you need in solution to form something close to a monolayer on the surface of these droplets dispersed in the aqueous solution. And indeed, if you look at SDS, the example I showed you at the beginning of my talk, you see also that it needs to be present in the microgram per mil concentration range. And so for DOPC and SDS, the 3 other lipids I show on this slide, we see configurational transitions which are consistent with changes in anchoring energies, close to saturation surface coverage on the drop. Lipid A is peculiar, and we're seeing something going on which is occurring at about 6 orders of magnitude lower concentration. So tremendously different response to the specific lipid structure. So we wanted to try and understand, why is it that we see this sensitivity to lipid A, and it's only seen in this droplet geometry. And so there's something about the confinement of the liquid crystal in this droplet geometry that is predisposing the system to go through a configurational transition in the presence of that lipid structure. And so we went back and looked at the literature dealing with liquid crystalline droplets, and it's a very large literature, goes back to work that was driven by the goal of creating polymer dispersed liquid crystal displays in the 80s and 90s. And so in that literature, typically the droplet of liquid crystal is dispersed in a polymeric matrix. It's not in an aqueous solution, so it's in a different continuous medium. And then more recently, there have been a number of studies where droplets have been created with well-defined sizes in microfluidic systems, and I show one reference to some work from Dave Waits's group, and there are a number of other groups doing very nice work in this area. And one can certainly create droplets and study configurational transitions using microfluidic systems. The phenomena that is of interest to us actually occurs in droplets of size which are difficult to produce by microfluidics. And so what we did was we set out to see if we could test a prediction, which is in the literature, about how confinement should affect the configuration of an LC droplet. And I'll show you an experiment that we designed to do that. Let me first sort of just show you one prediction, and there are a number in this very large literature about what should happen as you decrease the size of a droplet. And so you would expect there to be some size-dependent configuration because the elastic and surface contributions to the free energy of the droplet scale differently with size. And so this is a very simple prediction. And so it says that if you have a droplet, so this is slide 16, if you have a droplet where the easy axis coincides with tangential anchoring, you'll have the bipolar configuration shown on the left. And the elastic free energy associated with the strain in that bipolar configuration will scale as the elastic constant times the radius, the size of the droplet. In contrast, the contribution of the surface anchoring energy will scale as the anchoring energy times the square of the radius, so with the surface area of the droplet. And so from that very simple scaling argument, you would predict that there would be some crossover at a size which is of the order of magnitude of the elastic modulus over the anchoring energy. And if you plop in typical values for these low molecular weight liquid crystals in water, you would predict that there should be some transition with droplets of order 1 micrometer in size. So for large droplets, you would predict that you would indeed have the bipolar configuration because of the dominating influence of the surface anchoring energy. As you decrease the droplet size, the elastic energy dominates the configuration. So to minimize the elastic energy, you would predict the homogeneous configuration, and so you're incurring an anchoring energy penalty. And so that is a prediction that we sort of set out to test. And so we did that by this experimental system, and we used this system because it provided us with access to relatively small droplet sizes. And so let me sort of introduce it to you quickly. So we start off with monodispersed particles of silica, and those are commercially available with a remarkably tight control over size. And so that's a template. And so we can purchase those with sizes from 100 nanometers, plus or minus 10 nanometers, up to 10 micrometers, plus or minus 0.1 of a micrometer. So you can get them in a range of sizes. We then, and so we deposited through sequential adsorption so-called multi-layers. And so this is a phenomenon and sort of technology now that has been widely explored. Our collaborator, Frank Caruso, has a history of fabricating polymeric capsules through this technique. And so you sequentially adsorb polystyrene sulfonate, so an anionic polyelectrolyte. You then rinse the particle. You then adsorb a layer of polyallylamine hydrochloride, so a cationic polyelectrolyte. And you repeat that process 10 times. And what you end up creating on the surface of this silica particle is a thin polymeric capsule. You then expose that polymeric capsule to hydrofluoric acid and water, and it etches away the silica core. And so you end up with a hollow polymeric capsule, which is of the size of the template particle. So you have strict control over size. And in all of these experiments, we know that the surface chemistry that confines the droplet of liquid crystal is also held constant. And so after making the polymeric capsule, we fill it with 5CV. And I will skip how we fill it with 5CV. It's a simple process involving phase transfer between a bulk liquid crystal and an aqueous phase. But what we can create is shown at the bottom as droplets of liquid crystal of size that's controlled by the size of the silica template particle. And each of these droplets is wrapped in a thin polymeric capsule with a thickness of about a few tens of nanometers. And so we wanted to see what type of ordering was observed as a function of the size of the confined droplet, and to see whether we see this transition that is predicted by the simple scaling argument. And so what we saw experimentally is summarized at the bottom. And so for large droplets, we see the bipolar configuration, and by large I mean droplets larger than about 3 micrometers in size. But as you decrease the size of the polymeric capsule and the confinement of the liquid crystal, you don't see a transition to a uniform droplet structure, but what we see experimentally is a transition to the radial configuration. And at intermediate sizes between about 700 nanometers and 3 micrometers, you see a pre-radial configuration. And so this progression as a function of size, which is seen here inside these polymeric capsules, is something that we've reproduced now in a number of systems. And it includes droplets of 5CV dispersed in water. And so if you have the right homogenizer and conditions of sonication, you can produce very small droplets, and you can see the same transition occurring. So it's a general progression that we see as a function of size in these aqueous systems. And so why? And so this is an offering of an idea as to why we see it. And we think it may be associated with the role of K24. And so the argument that I presented before considered just one elastic constant to describe the elastic energy in the system. But if you look at the papers summarized at the bottom of this slide and calculate the contribution to the elastic free energy of the droplets in the bipolar and radial configurations, so this is the radial configuration, this is the bipolar configuration, you see that there's a contribution that comes from K24, and that contribution stabilizes, so makes a larger negative contribution to the free energy of the radial configuration relative to the bipolar configuration. And so if K24 is larger than 1.5 times K11 in the simple sort of order of magnitude description of the free energy, then you can predict that K24 will stabilize the radial configuration and that there will be a crossover at a critical size, which is given by this difference between K24 and K11. And so what you are probably also aware is that there's a stability limit, the Ericsson stability limit, that prescribes that K24 cannot be larger than 1.53 K11. So there's a very narrow band where one can predict that, of values of K24, where one can predict that K24 can stabilize this configuration. So it's a hypothesis that is consistent with our experimental observations and can account for this transition from the bipolar configuration to the radial configuration with decreasing size. And so what you would also notice is that this transition that occurs with size is the transition that is being triggered by the endotoxin, so on slide 20. And so the question then becomes is the reason that we see this sensitivity to endotoxin in part because the system is predisposed to this transition by the presence and influence of K24. And so if that's true, then we should see a strong size dependence in the response of the system to endotoxin. And so that's what we sort of went back and looked at. And so this is now showing the response of liquid crystalline droplets, slide 21, to 100 picograms per mil of endotoxin as a function of the size of the liquid crystalline droplets. And so I'm plotting here the fraction of droplets observed in the radial configuration, so to have been triggered to undergo a configurational transition by the endotoxin. And then the open bars, or white bars, are control experiments performed in the absence of endotoxin. And so indeed what you see is that the response to endotoxin is strongly size dependent. And so it's suggesting that the sensitivity that we see in these droplet systems is associated with this size-dependent configurational transition that we are tentatively suggesting may be related to K24, and I'll come back to that a little bit later. And so that's also sort of supported by going back to a planar interface. If you go back to a planar film, again stabilized in a TEM grid, you don't see a response to endotoxin until you get it to concentrations where you saturate the surface and you drive an anchoring transition by almost monolayer coverage. And so our sort of proposition is that K24 predisposes the droplets to the type of configurational transition that the endotoxin drives. And so this is a useful observation also in terms of providing an estimate of the magnitude by which the endotoxin perturbs the free energy of the droplet.
Which
and so what we can,
Nick?
Oh, if we can go to 24 now, slide 24.
Yeah.
So if we go to droplets of diameter 10 micrometers, what we're saying is that there's an imbalance in the contribution of the elastic and surface anchoring energy to the overall free energy that's sufficiently large that the endotoxin cannot overcome that imbalance and trigger the radial configuration. And so if we plug into that expression at the top, the values of anchoring energy, so of order 10 to the minus 6, we put in K24 equals 1.53 times K11 as our best sort of estimate, then what we can do is we can calculate the magnitude of that free energy term, and we know that the endotoxin cannot overcome that difference. And so that corresponds to about 10 to the minus 17 joules. So that puts an upper bound on the influence of the endotoxin on the free energy of these droplets. And so what does that number mean? And so going to slide 25. So if you measure the critical aggregation concentration of endotoxin and their values in the literature, it's around 10 micrograms per mil. And so from that critical aggregation concentration, you can calculate a standard free energy of transfer of an endotoxin molecule from being singly dispersed in aqueous solution into an aggregated state. And so that number, if you multiply it by a number of 700, so 700 endotoxin molecules, corresponds to about 10 to the minus 17 joules. And so what we are suggesting is that that free energy driving force that triggers the configurational transition is of an order of magnitude that can be accomplished by bringing together 700 endotoxin molecules. And that's roughly the sensitivity of the experiment to endotoxin. We see that of order 1,000 endotoxin molecules can trigger the configurational transition in the liquid crystalline droplet. So the key point is that the driving force needed to affect this configurational transition can come from the association of order 1,000 endotoxin molecules, and that's consistent with our observation regarding the sensitivity of the system. So I haven't said anything about where that self-association is occurring yet, but what we're suggesting is that there's a process of self-assembly going on between the liquid crystal and the endotoxin in this system. And so our very simple sort of summary of understanding of what's going on in this system, or proposition at least, is summarized in slide 27 with the yellow highlight. And so what we know is that delta F endotoxin is of order 10 to the minus 17 joules, and that we know as a function of size, we can perturb this free energy associated with the transformation from the bipolar to radial state. We should also be able to perturb it by changing the anchoring energy, if this description is correct. And so, as I mentioned earlier, in these aqueous dispersions of liquid crystal, you have ions present, and there are ionic phenomena occurring at the interface of the droplets. And those ionic phenomena, as I'll show you, influence the anchoring energy of the liquid crystal. And so that provides us with a way to manipulate the anchoring energy, and that's through controlling the presence of electrical double layers at the interface. And so on slide 29, I'm sort of showing what we have demonstrated in a couple of papers, and that is that at the interface between the aqueous solution, and it contains ions, and the liquid crystals, you have electrical double layers present. And if you flip forward to slide 30, these are some zeta potential measurements that we've done for droplets of liquid crystal dispersed in aqueous solutions as a function of pH. And so the zeta potential, so this is the potential you measure at the sort of hydrodynamic shear plane as the droplet diffuses or migrates under the influence of an electric field through the aqueous solution. It is of order tens of millivolts. And so there are phenomena that lead to the charging of these interfaces. And one hypothesis, which is in the literature, is that there's a preferential absorption of hydroxide ions to the interface. And indeed, as shown here, and there's a large literature with isotropic oils, you see that as a function of pH, the charging of the interface changes. And so if we go back to slide 29, so what we have shown is that that interfacial charge that accumulates gives rise to an electrical double layer. And in the zeta potential measurements I was just describing, we're characterizing the electrical double layer on the aqueous side of the interface, but the ions also partition into the liquid crystal. And so you form electrical double layers on the liquid crystal side of the interface. And we've measured the ion concentrations on that side, and in the two publications in Langmuir, we have documented the presence and structure of the double layer on the liquid crystal side of the interface. But the key point is that in the diffuse part of that electrical double layer, you have an electric field that's perpendicular to the interface. And with a liquid crystal with a positive dielectric anisotropy, such as 5 CV, that electric field associated with the internal double layer poles the liquid crystal perpendicular to the interface. And so the electrical double layer can trigger an anchoring transition to the homeotropic orientation if you add sufficient salt and go to sufficiently high pH in these systems. And so we can use this double layer to manipulate the anchoring energy of the liquid crystal and predispose the liquid crystal to assume the perpendicular orientation that is caused by the presence of the endotoxin. So if you go to slide 31, that is what is being demonstrated here, and it's described in a soft matter paper we published earlier this year. It's showing the effect of the ionic strength of the aqueous solution surrounding the droplets and the pH of the aqueous solution on the response of the droplets to 10 picograms per mil of endotoxin. And so if you just look at the left one, for example, what you see is that as you increase the ionic strength, a larger fraction of the droplets in the presence of endotoxin are exhibiting the radial configuration. And that's because as you increase the ionic strength of the aqueous solution, you increase the concentration of ions in the liquid crystal. That decreases the Debye screening length, that increases the strength of the electric field within the diffuse part of the double layer, and that electric field makes a contribution to the anchoring energy that goes as the square of the strength of the electric field. And so this result is consistent with the role of the anchoring energy in the expression that I've shown in the yellow at the bottom. And so to sort of summarize, we have experimental observations which are sort of consistent with this expression in terms of describing the effect of the size of the droplets and the anchoring energy on the endotoxin-triggered anchoring transition, okay? And so slide 32, the question sort of remains still is really what is the origin of that 10 to the minus 17 joules which drives the configurational transition that we see. And so what we know is that it occurs with endotoxin, but it doesn't occur with the other lipids. And so slide 33 summarizes some past studies of the self-assembly of endotoxin. And so these are phase diagrams that have been mapped out using small angle X-ray scattering. And what I want to really sort of highlight here is that if you look at the phase diagram at, say, 80 weight% water, and you go up in temperature, the region of the phase diagram with the diagonal lines, that's the melting of the tails of the lipid A of endotoxin, and this is from Salmonella. And the Q indicates the cubic phase. And as you go higher in temperature, what you see is ultimately a transition to a hexagonal phase, and it's an inverse hexagonal phase. And the reason that it's an inverse hexagonal phase is that as the tails of the lipid A melt, and this is what's sort of being depicted on the left side of this figure, is that they promote a shape of the endotoxin molecule that has a negative spontaneous curvature. So it would like to pack into aggregate structures that have associated with it a negative curvature. And so that would be something like an inverse micelle, for example. And so if we perhaps go to slide 35, to skip 34, it's not needed. If we look at the other three lipids that I was using as points of comparison for SDS, so SDS in aqueous solution under the solution conditions that we typically use, SDS forms aggregates which are associated with a spontaneous curvature that is positive, so it will form normal micelles. And DLPC and DPPC also have spontaneous curvatures. They're actually very close to zero. They tend to form lamellar structures, but they're not negative like endotoxin. And so the distinguishing sort of characteristic of lipid A, and it's seen both for lipid A and endotoxin, they both form that inverse hexagonal phase at high temperatures. It's common to both of them, is the negative spontaneous curvature. And so our sort of proposition is that what distinguishes lipid A from the other lipids that we've looked at is this negative curvature, and that would be a tendency to form inverted aggregate type structures. And so what we are sort of hypothesizing is that the endotoxin self-associates with the liquid crystal to form some type of assembly that has a negative curvature associated with it. And so that would be something like an inverted micelle. And so we don't have structural evidence of that. And so that's a hypothesis, it's a proposition. But we do have on slide 37 some confocal fluorescence microscopy that does show evidence of internalization of endotoxin. And so that's what's shown on the left. It's a fluorescence micrograph, and it's actually obtained at a relatively high endotoxin concentration in order to have sufficient contrast. And it's a fluorescently labeled, BODIPI labeled endotoxin. But if you look at the center of that confocal image of the droplet, you see that there is a bright core. And so there is accumulation of endotoxin within the liquid crystalline droplet. And if you bleach that dye, so if you subject the BODIPI fluorophore to a high level of light, intensity of light, you can bleach it. And that's what's being shown in the right plots. It's probably hard to decipher, but we're showing the bleaching of the fluorophore, and then we remove the illuminating light source, and what we see is we see the fluorescence recover. So there is exchange of endotoxin going on between the center of that liquid crystalline drop, which is in a radial configuration, and the surface of the liquid crystalline drop. And so this is a observation, it's not proof, but it's consistent with the idea that there is uptake of lipid A and endotoxin into these droplets, and that we see localization of the lipid at the site of the point defect of the droplet. So I think what I'll do is I'll just quickly wrap up at this point. And what I do want to tell you is that we have a number of other observations which are consistent with the idea that these configurational transitions caused by endotoxin at low concentrations are not driven by changes in surface anchoring energy. And one set of observations relates to the transition states that we see between the bipolar and radial configurations. So this is the set of transition states that you see, slide 38, with STS, which is a transition driven by surface anchoring energy. If you go to high concentrations of endotoxin, where you have sufficient endotoxin to saturate the surface of the droplets, you see the same set of transition states consistent with a configurational transition driven by a change in anchoring energy. If you go to the picogram per mil, you see a different set of configurational states, and what you don't see is the disclination loop that characterizes the surface anchoring transition. So there are other pieces of evidence that certainly support the idea that it's not a surface anchoring transition, and I think I'll skip that. And so let me just sort of summarize by saying from a technological perspective, these droplet systems look very interesting in terms of forming the basis of methods of detecting specific biological lipids. And what we see is a selectivity to endotoxin, which and a sensitivity that we haven't seen yet with any other lipid. We only see it in a range of droplet sizes where the droplet is sort of on the edge of undergoing a transition to the radial state. And so it's this droplet size range where we believe that there's a balance between elastic and surface contributions to the free energy. So it makes the bipolar and radial states almost energetically degenerate. And our experimental observation suggests that we're not looking at a surface anchoring energy-driven transition, but there's some type of localized association or self-assembly of the lipid A with the 5-ZB, and we see localization of the lipid A at the center of these droplets. And we believe that's the driving force for the configurational transition. So there's lots of things which are not yet resolved. And so one question is really whether this size-dependent phenomenon is due to K24. I mean, our little order of magnitudes of analysis of the energetics only predicts the transition for a very narrow range of values of K24. And so, is there something else that's contributing to the stabilization of the radial configuration for small droplets? If you calculate the device screening lengths associated with the ions that partition into the liquid crystal, the device screening lengths are of order 100 nanometers. So they're not that much smaller than the radius of these droplets, and so might there be size-dependent phenomena associated with the double layers occurring inside these droplets, and perhaps that's playing some role in the phenomenon that we see. And then finally, our observations at least are consistent with the idea that there's some type of self-assembly of lipid A occurring within the liquid crystal. And we have a thrust of research now that's looking at sort of the generality of that, and we see evidence of self-assembly of other lipids at other types of defects. And so that's an area which I think is actually very fertile one. I think the environment of the defect provides a different set of solvent properties for self-assembly to occur within. And so I'll finish just by acknowledging the students who've been involved in the work. We have a number of collaborators, in particular Frank Caruso played a key role in some of our experiments here, and we're grateful for the sponsorship of the research, and thank you very much for attending the seminar.
Well, thank you, Nick. Fascinating talk, most enjoyable. Will you entertain some more questions? Questions from the audience? Yes, Tim.
Well, can't you study flat surfaces directly? Right, I mean, you've been speculating about anchoring transitions, and can't you study simply flat surface between a liquid crystal and the liquid crystal of water, which presumably phase separates, and dribble small amounts of your endotoxin in and see whether they are giving rise to some anchoring transitions?
Yeah, so we, and I think sort of I would say we have to some extent, and so we have looked at anchoring transitions driven by endotoxin at planar interfaces, and our conclusion is that if you want to drive the change in orientation of the liquid crystal at a planar interface through a change in anchoring energy, then you need a surface concentration of endotoxin, which is not very different from SDS. You have to have almost saturation coverage in order to change the anchoring energy. And so in that respect, endotoxin is unremarkable. It's like any other amplifier. And what we're seeing in these droplet systems is that actually the anchoring energy is not what's really driving the configurational transition. The anchoring energy is important in putting the system on the edge of this transition between the bipolar and radial state, but we don't believe that the endotoxin is driving the transition by changing the anchoring energy at all. Its concentration is 5 orders of magnitude below that, at which we see the anchoring transition occur in the droplet system. What I would say is, and maybe this comes to your point, is that perhaps there are other experimental geometries where one can also put the system at sort of the edge of going between configurational transitions, and under those conditions one might also see the same sort of thing that's going on in these droplet systems. So if you get a system that has two states which are almost energetically degenerate, then a small change in another part of the free energy may drive the change between states.
We have another question from Buddha Chakrabarti from Durham University.
Hi, sorry, I seem to have read somewhere that, you know, measuring K24 is very hard, and maybe others in the audience know better. I mean, do you have even sometimes even the sign is probably not known, and it's only being measured in sort of lyotropic liquid.
Actually, I'm only picking up about half of what you're saying.
Okay, so I'm saying that, you know, I seem to recall that it's only been sort of measured in some lyotropic systems, but so do you have an estimate for this K24, or have you measured it, and if so?
So I think that measuring K24 is very difficult, and we have sort of dug our way through the literature looking for experimental estimates, and there are experimental estimates and estimates based, for example, on confinement of liquid crystals within a cylindrical geometry, where you form an escape radial defect. And actually some of the experimental estimates that pop out of those papers violate the Ericsson stability limit. So, for example, I've seen values of 3.3 times K11. I think that in those systems there are probably other contributions to the free energy, and for example flexoelectric effects may be important, and I know that Slobodan Zuna, who I see sitting over there, has been thinking about the role of flexoelectricity and stabilization of the radial configuration of droplets. So I suspect some of the prior experimental estimates are incorrect because there are other contributions to the free energy that were not considered when the K24 values were extracted from experiments. So I'm not aware of good experimental values.
So in your theory, what value do you use? I mean, in your free energy expression, what value of K24 do you use?
We put in 1.53 K11, and it's the value that corresponds to the Ericsson limit. It was the largest one that we could possibly justify. If it's less than 1.5 K11, it won't, according to our simple energy argument, it won't stabilize the radial configuration.
Another question here, Samir.
You see that your endotoxin goes to the cores of the VEX. It goes to the core of the VEX.
That's our proposition, and our confocal microscopy does provide some support for that.
Yeah, because my colleagues measured, for example, transition to blue phases and to TGP, and they trigger it by adding nanoparticles. So, and in this case, this transition is enabled by core replacement mechanism. So if you
actually, I think not. So if you make an estimate of the free energy of the core of the defect, it's around 10 to the minus 19 joules. And so the driving force that we see is around 10 to the minus 17 joules. So I think that the core replacement actually is a very small part of the free energy driving force. And I think that with our tentative conclusion is that the driving force really is coming from the self-association of the endotoxin molecules. That's of order 10 to the minus 17 joules, so 100 times larger.
Dr. Schumer's got a question.
I think a question related to the K24 it should be is a general one which is related to any kind of surfactants which you use. So therefore, if these things occur just with the endotoxin, while the others are not, so there were no other examples, that means that there must be a clue certainly in this endotoxin. K24 can perhaps help that the system is closer to the border of the transition between one state and another state. But as we are talking about this condensation of these molecules in the center, certainly they then cover a part of this high energetic core, but perhaps there is more. There could be a kind of seed which promotes certain anchoring in the center. So somehow promoting a central area like a kind of hedgehog structure, which perhaps is a mixture of endotoxin and some other molecules from the liquid crystal. And this association can perhaps help to stabilize there. But that's it.
I agree, and also myself in the center. And so it's, that's our sort of working hypothesis, is that there's some sort of inverted self-assembled structure, and there may well be some amount of water in a pool in the middle, and that may be decorated by the lipid A. So that's, I think what you're saying is consistent with at least our imagination.
And if you bring some water in, then it's also bigger. So that also takes more space than a simple core of the defect.
Yeah, that's right. I mean, we would love to have some structural characterization of the center of the droplet. It's a very difficult problem. We're trying now to do some cryo, CEM, of lipids in defects, not yet the droplet geometry, but just creating disclination lines and looking at the partitioning of lipids into them. And lipids do partition into them. And we're trying to use cryo-TEM to see what sorts of self-assembled structures form in the defects. But it's a very tough problem. If people have ideas of how to do it, we would welcome them.
Epifanio Virga has a question.
Nick, don't you think that the number of tails, which is larger in this case, could enhance the affinity of those little molecules to the center of the hedgehog? Yeah,
I think that's correct. And so the CAC that I reported in the microgram per mil range for surfactants, the critical micelle concentration of SDS is around 7 millimolar, so it's many orders of magnitude higher. So that 10 to the minus 17 joules that I keep mentioning, that indeed includes what you were just referring to. So the fact that there are 6 tails means that the critical aggregation concentration is low. That makes a large free energy contribution as the...
Just as to the volume estimate.
Yeah. Yeah, in fact, what's also interesting is that if you look across bacteria, the structure of lipid A is actually not preserved. So actually Salmonella has 7 tails, E. coli has 6. And we have now looked just recently at both Salmonella and E. coli, and we do see the configurational transition with...
Oh, oops. Hello?
It's gone. I got to book some time.
We seem to
By a satellite or...
yeah, I guess so. Apparently, they had a timer on their end.